Hello everyone, welcome to today's video. We're going to be covering binary search trees from scratch. So if you have no idea about binary search trees, this is the video for you. And if you do have an idea but you need to reinforce what you already know, or you have some weak spots or some gaps, this is also the place for you. Okay, cool. So first of all, let me walk you through a scenario, right? Let's say, for example, you had 100 books, right? And you were looking for the 67th book amongst these 100 books, right? So, a way for us to find this book could be, we take each book one by one, until we find a specific book that we're looking for, right? Which is the 67th book. That will take 67 times to find the book that we're looking for, right? Let's even take this at a greater scale, right? Let's say we had 100 million books, right? And we were looking for the 700,000th book. That's going to take us 700,000 times until we find the book that we're looking for. That's way too slow. How binary search works is it uses some sort of algorithm, right, to find what the middle book is, right? And in our case here, it's number 50. And what we do is, okay, it checks if the number book that we're looking for is greater or less than 50. And since 67 is greater than 50, we ignore the entire left side, right? So now we start looking towards the right side. So what we do next is we look at, okay, what is the middle of 50 and 100, right? And we know that in the middle of 50 and 100 is 75. So what we do now is we ask ourselves, is 67 greater or less than 75? And we know 67 is less than 75, so we ignore the right side and we look towards the left, right? So now we look towards the left of, right, of 75. And if we look in the middle here, we'll find 62. And what you've seen here is we found book number 67 in 4 steps as opposed to 67 steps. And this is huge, right? Okay, so now let's think about the physicality of what a binary search tree would look like. But before we get to the tree itself, we need to understand what a singular node is, right? And a singular node is a number, right? Any sort of number that includes 2 arrows, okay? A left arrow, which points to a number that is less than the number itself, and a right arrow, which points to a number that is greater than the number itself, okay? That's pretty much it, okay? A node is the number itself pointing to another number on the left and also pointing to another number on the right. Okay, so let's take an example of a single node, okay? A node all by itself. So we have example here of number 10, right? And in this case here, number 10 on the left side is pointing to null, and number 10 on the right side is pointing to null as well. So this means number 10 has no children, and both of the arrows are pointing nowhere. And in Java, this would be represented just like this. So we have our class of our tree node, and we're setting our number here, right, variable, right? We're initializing it, and we're also giving our tree node a left arrow and also a right arrow. And in here we have our constructor, and we're setting it to val equals val, and we're setting our left arrow to null and our right arrow to null. Okay, very, very simple stuff here. Okay, this is something here that you're going to have to get stuck into your head, right? Because this is kind of the placeholder for other types of data structures like linked lists. It's very similar to graphs, doobly linked lists. So once you can understand what's going on in here, right? Once you move over to other tougher concepts, a walk in the park. Okay, so once we have this part here, in our main method, we are going to have tree node. We are going to have tree node indicating this is, this is the object. So once we have our constructors and our class setup, we're going to have our object, which is our tree node, and we're going to name our tree node my node equaling our new object, which is new tree node, and the value in our new tree node would be 10, right? And remember, this new tree node here, the value here is 10, right? Because remember, we're declaring our int value as number 10, and it is also pointing to null on the left side, and it's also pointing to null on the right side, right? Cool. So now let's connect the nodes to each other. So we're just going to start off by creating tree nodes, okay? So we have node A, node B, and node C. And we're going to create them with tree numbers 10, 5, and 15, okay? So once we have 10, 5, and 15, what we want to do is we want to have 10 to point towards 5 on the left side and point towards 15 on the right side. So how we do it is we're going to have A. And remember, A is our roots node, okay? And we're going to do A dot left, right, equals B, okay? And B is our number 5 here. So that gives us 10 pointing to 5 on the left side. And if we want 10 to point to 15 on the right side, we do A dot right equals C. And remember, C is number 15 here. And pretty much that gives us the shape over here of our first binary search tree. Okay, so now let's say we wanted to add a couple more nodes to our tree, right? So what we do is we create 2 more just like this, and we're going to name it D, and we're going to name it E, and we're going to give them the value of 2 and 7. And just like we did before, we have B dot left equals D and B dot right equals E. And now it's going to look just like this, okay? This is our B, and B on the left side is pointing to number 2, and remember number 2 is D, and on the right side is pointing to 7, okay? And remember, this is our root, right? Our root is where everything starts from. And the children of 10 would be 5 and 15, and the children of 5 would be 2 and 7. And 2, 7, and 15 are called leaves because they have no children. Perfect. Okay, so now, not every tree is a binary search tree, right? A binary search tree is only a binary search tree if it follows this specific rule. So everything on the left side needs to be a smaller value than the number itself, and everything on the right side needs to be a bigger value, right? So let's verify if the tree that we just created is a binary search tree or not. So we can see that 5 is less than 10, so it's on the left side, and we can see 15 is greater than 10, so it's on the right side. Once again, for 5, we can see that 2 is less than 5, so it's on the left side, and 7 is greater than 5, so it's on the right side. Very, very simple stuff here, guys. So let's take an example of something that is not a binary search tree. So we can see that 12 here already, right, is bigger than 10. So since 12 is bigger than 10, it has no reason being on the left side. It should have never been here. It should be right over here, okay? It should be on the right side of 10, okay? Cool. So now, let's take an example of, let's say we wanted to create some sort of algorithm to look for a specific value inside of our binary search tree. So let's say we wanted to find the number 7, right, in the binary search tree. So without looking at any code, we're just going to understand what goes on, okay? So first of all, we have our root, right? And our root is 10. So we want to find 7. So we check, okay, is 7 equal to 10, right? Is our root equal to the number that we're looking for? Since it's no, we move on to our next instruction, which is 7 less than 10? And we know 7 is less than 10, so we go towards the left. So we were here before, and now we're here. We're at 5. So now I'm at 5, and I want 7. Is 7 equal to 5? No. So next we're going to do, is 7 greater than 5? Yes, 7 is greater than 5, so we go towards the right. So now we're here. This is where we are. Now I'm at 7. I want 7. Is 7 equal to 7? Yes, it is, so I have found it, okay? So once again, we can see that we were able to find number 7 without looking at every single node, okay? And if we wanted to look for a number that is not inside of our binary search tree, it should bring us all the way to null. For example, let's say we had 99 and we wanted to look at each level. Hey, is 99 greater or less than 10? Since it's greater, we look here. Look here, which is the right side. Is 15 greater or less than 99? We know 15 is less than 99, so we go towards the right. And we can see that there is nothing here. So now we are at null. And now, since we're at null, we know it doesn't exist because we were not able to find our number. Okay, so now I'm going to show you guys the code for searching within a binary tree. Okay, so first of all, like usual, we have our tree node, right? And we're going to implement a search method. And our constraints, right, our parentheses would be the node itself that we're working with, right? So in our case, we'll put our roots, right? So for the case of this example here, we would have 10, okay? So 10 would be our node, and our target would be 7, right? So we're looking for 7. So let's say, for example, yeah. So now let's jump into what's inside of the code itself. So we check, is the node that we are on currently equal to null? If it is equal to null, we return no. Since it's not, right, in our case, because we're looking for 7, we continue onwards. So now, if our target is equal to our node.val, right, which is the node that we're on's value, we return the node itself that we are on. Right? So these are our first two checks, okay? And then if none of these are true, we move on to the next. So if our target, right, and remember our target in this case is 7, if 7 is less than our node.val, right, which is the node that we're on, right, because remember, we start from 10, so our node.val will be 10. We return this method itself, search node.left, comma target, right? So node.left so what we're doing here is we are telling it to go towards the left, and our target is remaining the same, okay? And it continues this search here. And if it is not, if our target is not, we move on to our next check, which is if it's bigger, right? So we return our search node.right, comma target. So what we're doing here is if it is bigger, right? Because if it's not less, it's obviously bigger, right? What we do is we return the whole algorithm again, but we go towards the right side, okay? We go towards the right, and then we just continue searching. Is it null? Because if it's null, remember, we've reached the edge of a tree and it doesn't exist. And if it does exist, we return the node itself, okay? Very simple stuff here, guys. So just to go over that one more time, right? It's what we're doing here is we're doing the same thing again, but we are starting from the left child, okay? Because the node that we are on, but instead of staying on this node, we go towards the left. So that means, for example, here, if we're on 10, it will do node.left, which would be 5 now. So 5, it moves on to 5, and our target will still remain as 7, okay? And that's if it's smaller, right? But if it's bigger, right, it moves towards the right. So our new node would be 15, okay? And we return this to do the same thing again, to do the same method again. Check these two, and this in here, and that in here as well. Just to walk you guys through the example, we have search. So if we're searching for, and we're starting from our root of 10, right, and our target is 7, we ask, hey 10, do you have 7? No, it's not, but 7 is less than 10, so ask left child, right? And this is our left child here. So remember, our target that we're looking for is 7, and the node we're on is 10, okay? And since 7 is less than 10, we return. So we start this whole method all over again, right? So we're returning the method itself, but instead of starting on 10, we go node.left, which is moving it moving from 10 to 5, right? Moving from 10 to 5. And now we're checking node equals to null. So node is null, it's 5. And our target is 7 equal to 5. Because remember, we've moved from 10 to 5. Okay? And since we check, okay, is 5 less than 10? Since it's not, we move on to this one here. Since it's bigger. Because if it's not less, it's bigger, right? Okay. Yeah, so that pretty much should explain that part.